We are mapping the absolute physical boundaries of the observable universe, the limits where the laws of rotation and temperature reach their breaking point. This graph plots rotational frequency against temperature. Earth is our baseline at 10 to the negative 5 Hz and 300 Kelvin. Populating it with extreme entities, pulsars, quasars, accelerators, expands the scale by trillions. The data pulls into two distinct islands, top right and bottom left. The existence of these two islands suggests that a star's rotation and temperature depend heavily on its immediate surroundings. The upper cluster is defined by active accreting environments. In these systems, matter siphons from a companion star onto a dense core, injecting massive amounts of energy and angular momentum. The lower cluster represents the isolated resting state of stellar corpses, dead stars cut off from any external fuel, left to cool and slow down in the vacuum. Between these states, a set of thermodynamic and mechanical laws acts as a cosmic governor, a hard ceiling that prevents these systems from spinning or heating up indefinitely. We can map the boundaries of physics by observing how accretion systems fight against these governors and how isolated systems succumb to them. Reaching the records of the universe requires understanding the exact mechanisms of this matter transfer. On the rotational axis, the fastest natural objects known are PSR J1748-2446 AD and 4U 1820-30. Although they are different types of neutron stars, they both peak at a rotational frequency of exactly 716 Hz. At 716 rotations per second, the equator of a city-sized star moves at 24. Mathematically, a neutron star reaches its breakup limit between 1000 and 1200 Hz. At that point, the centrifugal vector overtakes gravity and the star shatters. However, our observed data hits a ceiling at 716 Hz. Something is stopping the rotation long before the star reaches its physical breaking point. That ceiling is likely the emission of gravitational waves. As a star approaches 716 Hz, any slight asymmetry in its crust begins to churn the fabric of spacetime. This radiates energy outward, acting as a brake that bleeds off angular momentum before the star can tear itself apart. Mechanical integrity and gravitational radiation create a hard speed limit that mass alone cannot override. No lone star can reach 716 Hz on its own. Reaching the limit requires an external torque source, a process called recycling. On the left, we see the recycling mechanism in action. PSR J1748 siphons gas from a red dwarf companion, while 4U 1820-30 strips matter from a white dwarf in an 11-minute orbit. This stolen matter provides the torque to spin up the core. On the right is the alternative, the Magnificent Seven. This is a group of isolated neutron stars with no binary companion. Lacking a source of external torque, these stars emit steady thermal X-rays and rotate slowly, with periods between 3 and 12 seconds. Without stolen matter to maintain the speed, isolation defaults to rotational decay. We see similar constraints when we pivot to the temperature axis. Nature's thermal peak for a stellar body occurs at the moment of core collapse. A newborn neutron star briefly reaches 100 billion Kelvin. Without an active fuel source, mature stars cool down rapidly from this peak. To study temperatures beyond this natural decay, researchers at CERN use high-energy physics to recreate the conditions of the early universe. This is the site of the ALICE experiment at the Large Hadron Collider. Inside these detector arrays, lead ions are smashed together at nearly the speed of light. These collisions reached 5.5 trillion degrees Celsius. That is roughly 250,000 times hotter than the center of the sun. For a fraction of a second, this fireball mimics the quark-gluon plasma state of the universe immediately following the Big Bang. This man-made record is transient. To find a sustained natural extreme, we must look for a system with a continuous energy source. That system is Quasar 3C273. Powered by a supermassive black hole with the mass of 900 million suns, its accretion disk maintains a stable temperature of 40 trillion Kelvin. According to the inverse Compton limit, stable temperatures should cap at 100 billion degrees. This diagram shows the mechanism. At extreme temperatures, electrons move so fast they collide with their own emitted light. They transfer their energy to those photons and cool down, effectively choking out the heat. Quasar 3C273 bypasses this ceiling. The sheer volume of material in its accretion disk and relativistic jets provides a continuous injection of energy that overwhelms the inverse Compton cooling. Breaking thermodynamic ceilings requires the same continuous accretion seen in rotational records. Our parameter space is now complete. The thermal boundary sits at 40 trillion Kelvin, where massive accretion disks bypass standard radiation cooling. The rotational boundary sits at 716 Hz, where gravitational radiation halts acceleration before structural failure. Every object at these limits shares a single trait. They are actively consuming a companion or an accretion disk. Extreme speeds and temperatures are temporary anomalies. They depend on continuous mass transfer to stave off the physical governors of the universe. When the accretion fuel inevitably runs out, the parameter space shifts. The outliers fade. Without active consumption, the pulsars slow and the quasars gruel, leaving only the remnants in the bottom left corner. The Magnificent Seven represent the inevitable thermodynamic and mechanical destiny of the cosmos. While the universe's records are defined by the violent consumption of matter, its enduring nature is defined by isolated decay.